Hi, I'm Steve Sokol, founder of Falcon Avionics. In this training presentation, I'm going to cover the basics of using the FlightView application. We'll start out with a quick walkthrough of what FlightView is and how it works. Then we'll drill down into the specifics, covering each subsystem and screen. This presentation doesn't cover installation or configuration. We have separate presentations for each of those topics. Here's our basic agenda. The first section is a review of the main features and functions of FlightView. Next up is a walkthrough of the architecture, how the various parts of FlightView fit together. Then, a brief explanation of how to install the FlightView app. After that, we go through the main subsystems, one at a time, explaining how they work and how you use them. So first, the feature review. FlightView is an EFIS, an electronic flight information system. Now that term is used to cover a lot of different products, from basic digital instruments to highly integrated digital flight deck systems. FlightView is closer to the latter, a highly integrated digital flight deck system. It provides just about all the information you need to fly, other than what you get by looking out the window. At the top level, we have a complete set of flight instruments displayed using the popular Primary Flight Display, or PFD layout. This gives you the attitude, altitude, airspeed, and all the related information you need to operate safely. FlightView also has a complete engine monitoring system with alert capabilities, user-adjustable ranges, and support for a broad range of sensors, senders, and transducers. We also have integrated GPS navigation capabilities. Our MFD, or Multifunction Display, has a moving map to display your course. Behind the scenes, the Flight Data Computer, or FDC, has a navigation subsystem that feeds both the display and, optionally, an autopilot. The MFD also includes a wealth of situational awareness data: NEXRAD weather radar, current METARs, local air traffic, terrain, obstacles, and airspace. FlightView can drive any modern digital autopilot, and we have deep integration with the Bendix King X Cruise, formerly known as the TrueTrack Vision. Our autopilot integration offers GPS steering, often referred to as GPSS, that eliminates waypoint overshoot and makes for a more efficient course. COM radio integration allows you to load and activate frequencies at the touch of a button. And our transponder integration quickly allows you to key in a squawk code or trigger the ident function when requested. We also have an integrated checklist system that displays and optionally plays custom list items. And the whole system is configured using a simple set of controls. One last top-level feature that's worth mentioning is Jeeves, our virtual co-pilot. Say hello, Jeeves.
Hello, this is your co-pilot speaking. Today we will be cruising at warning terrain, warning terrain.
If you have an audio connection from your iPad, you'll hear Jeeves speak up whenever something's out of place: an engine sensor reading too high or too low, a potential traffic conflict, an upcoming obstacle, or anything else that might impact the safety of your flight. Jeeves also provides audio briefings for upcoming airports, reads off your checklists, and offers helpful reminders like switching tanks or lowering your landing gear. As you may already be aware, FlightView is built a bit differently from other EFIS products. We've basically unbundled the EFIS, breaking it into front-end display components and back-end data source components. Where the typical EFIS puts all of that into a single expensive custom display system, FlightView uses off-the-shelf Apple iPad tablets for the display, and a separate flight data computer as the core or hub of the system. This architecture has a number of real advantages. First, using off-the-shelf hardware is a much more cost-effective process than building custom display systems. It lets us use the best available technology, with faster processors, higher resolution displays, and more memory than any low-volume custom system would have. Because the system is just a tablet running an app, adding additional cockpit displays is as simple as adding iPads. This reduces the cost to as low as $300 for each additional display. The modular design of FlightView also makes it much easier to install than the typical EFIS. Wherever possible, we use modern digital interconnects rather than dozens or hundreds of individual wires. A typical installation takes about 20 hours and doesn't require many specialized tools. Finally, because each iPad is a full computer with its own battery, processors, etc., we have a degree of redundancy not available in most EFIS products. If you lose ship's power, shutting down the back-end components, the application will switch over to a reversionary mode, using the iPad's GPS, barometric sensor, and other onboard capabilities to provide a critical subset of flight and navigation information. Okay, on to the next section, installing the FlightView app. If you order one of our ready-to-fly kits, you can skip this, as the iPad comes with the app already installed. If not, you can easily install it from the Apple App Store. Just make sure your iPad is connected to the internet, launch the App Store app, and use the search function, that's the magnifying glass, to search for FlightView EFIS. Once you've found the FlightView app, tap the Get or Download button to start the installation. The app is about 100 megabytes and should take about a minute or less to download on most broadband connections. Once the app is downloaded, you can launch it from the App Store app or by going out to the home screen and tapping the icon. The first time the app runs, it will launch an onboarding tool called a Setup Assistant. The Setup Assistant will walk you through getting started. When you see the initial welcome screen, tap the Next button. The first step is to either log into the application if you already have FlightView credentials, or to select the 30-day free trial. FlightView credentials are available for free to anyone who purchases a FlightView hardware kit. If you've purchased a hardware kit and need to get credentials, go to the Falcon website, navigate to the support page, and find the link labeled Request FlightView Credentials. Fill out that form with the requested information, and we will email your credentials usually within about 24 hours. If you don't have credentials and want to try out FlightView, you can use the 30-day trial. The 30-day trial comes with a few limitations, including a limited number of base map downloads and a few features that are disabled. What's included is more than enough to give the app a quick checkout, especially if you don't have the hardware. One important note, the free trial only works once, ever, on any given iPad. Even if you completely factory default the iPad, you won't be able to get a second free trial running on that iPad. Once you've either logged in or opted for the trial, you'll need to grant the app permission to access several subsystems on the iPad. First, the Setup Assistant will prompt you to grant permissions for location services. We use location services as a backup to the FlightView hardware. If your iPad has a GPS, enabling this will allow FlightView to use that GPS. When the dialog box appears, please select the Allow While Using App option. Later, iOS will pop up another dialog asking if you want to give FlightView permission to use location data all the time. When that happens, please let it. That makes it much faster to switch over to the local GPS position if the FlightView GPS drops offline. The app will ask you about several other services, including push notifications, which we use to let the app know there are updates available, Bluetooth, which we use to connect to the flight bar controller, speech recognition, music library access, and local network access. The local network access option is especially important as it's required to connect to the FlightView FDC over Ethernet or Wi-Fi. If you don't grant access to local network resources, FlightView won't work. If you accidentally deny FlightView permission for local network access, you can fix that in the main iOS settings on the Privacy page. Once you've finished with the permissions for the system will prompt you to download the Aviation Database. This is the monthly data dump that contains all the airports, runways, frequencies, and other important data elements that make FlightView work. To download it, just tap the Download button. The database is about 200 megabytes and should take about a minute to download on most broadband connections. Next up is base map downloads. The way FlightView's mapping system works, we start out with a very low resolution map of the world, then layer detailed data on top of that. This step is optional, but I wouldn't skip over it unless you're in a big hurry. Without the base maps, all you'll see are very rough outlines of water features and a few aviation items that we add on top. It works, but you won't get terrain information. To add base maps, select the states where you fly by tapping them, then tap the Begin Download button. Don't worry, if you missed a state, you can always add that state from the Downloads page later on. Finally, you need to review and accept the FlightView Terms of Use and License Agreement. This details the legal obligations between you, or anyone who uses your aircraft with FlightView installed, and Falcon. It's not the usual yada yada. Failure to follow directions or follow best practices in an airplane can be hazardous to your health. So, look it over, and if you can live with the terms, tap the I accept button. If not, please exit out of the app and delete it from your iPad. Ah, good. Looks like you decided to stick with us. At this point, we're done with the Setup Assistant and ready to start using FlightView. Go ahead and tap the Let's Fly button to continue. When you tap that button, the system will start running the actual FlightView application. There's a lot that goes on in FlightView, and in the order that we start things up is fairly important. You'll see a bunch of different services listed as starting, and the startup process takes between 3 and 5 seconds. If you take a look at the bottom of the screen, you'll see a couple of important bits of information, the version and the build ID. If you ever need to open a trouble ticket, Make sure you know what version and build you're running, as it makes it much easier for us to figure out what's going on. After the launch screen disappears, you'll see the FlightView interface. Keep in mind that you're seeing it in standalone mode, with no data from the FlightView hardware to drive it. The default view is a split screen, with PFD on the left and MFD on the right. If your iPad has a GPS on board, and if that GPS has a good signal, you'll see ground speed, barometric altitude, all iPads have built-in pressure sensors, and basic location information. If you're connected to the internet, you may also see airports appear on the map with colored icons indicating the flight condition, which uses the FAA METAR data received over the internet. Before we dig into all the screens, it's worth taking a second to talk about the workflow you'll use with FlightView. Most users set up their system on the bench first before they install it in their aircraft, so we'll first do a word about that. To start out with, FlightView uses quite a bit of power since it stays in the foreground at all times, with several radios running and with the backlight cranked up. While you can run it on battery, if you're going to be using it for more than 30 to 45 minutes, we recommend you have an iPad plugged into a charger. To be able to configure back-end services, you'll want to connect the peripherals, the GPS receiver, air data computer, and engine monitor, to the FDC and power them up. The flight data computer and the engine monitor both require a power source. You can use either a 12-volt or a 28-volt source. A standard off-the-shelf 12-volt transformer capable of producing at least 1 amp of power should work. Once you've got them powered up, the FDC will create a Wi-Fi network. The SSID of that network will start out with Flightbox-EXP. You'll need to log into your iPad, go into Settings, and connect to that Wi-Fi network. If you look carefully at the Wi-Fi connection page, you may notice a small warning that the network has no internet connection. That is totally normal. That network connection is used to move data between FlightView and the iPad. No internet required. Once you have the Wi-Fi network connected, go back to the home screen and launch FlightView. Once the app starts up, it will automatically try to connect to the FDC. The first time this happens, you may be prompted to grant the app permission to access local network resources. Please say yes, otherwise the link won't work. The process for starting up is about the same in an actual airplane. Start by inserting your iPad into whatever mount you've opted to use and connect it up to the charger. Make sure the avionics master is switched off and then follow the standard procedure to start your engine. This reduces the chance of a spike or a brownout causing problems with your avionics. Once the engine is running, turn on the avionics master and boot up the FlightView system. Give the system a few seconds to boot up, and then, if you're using Wi-Fi, go into the iPad Settings app and make sure that the tablet is connected to the Flightbox-EXP Wi-Fi network. If you're using a wired Ethernet connection, you can skip this step. Finally, launch the FlightView app. Note that it can take a few seconds for the app and the back-end hardware to sync up. So now that you have FlightView installed and you know how to connect it to the hardware, let's take a closer look at the way the app works. Our goal is for everything in FlightView to be as intuitive and responsive as possible. In most cases, you should be able to figure out what's going on just by looking at and using the app. This section gives you a pretty good idea of how it all works. Okay, at the top of all FlightView screens is the status bar. This is always visible, and it provides a quick reference point for a number of pieces of critical information. On the left-hand side are status indicators related to critical hardware components. When the system is not connected to an FDC, you'll see a red triangle with an exclamation point next to the letters FDC. You don't see that in this screenshot because the FDC was connected when we took it. There are indicators for the FDC, the GPS receiver, and the ADS-B receivers. The middle section of the status bar shows clocks and the flight timer. In landscape mode, the system displays local time, Zulu time, and the duration of the current flight in hours and minutes. In portrait mode, we drop out the Zulu time clock and only display local. The flight duration timer automatically starts when the system detects a takeoff and stops when the aircraft lands. The right-hand section of the status bar shows the status of the COM radio or radios, the transponder, and the iPad itself. The two white headsets represent COM1 and COM2 respectively, and these show the current frequency for the associated radio. The transponder icon shows the mode, in this case on, and the current squawk code. Tapping on the transponder icon will cause the transponder to ident. At the rightmost edge is a battery indicator. The battery icon is green if the iPad is plugged into a power source, and white if it's running off of battery power. Another icon, not shown here, is a red thermometer. This indicates the iPad is experiencing thermal stress and should be cooled down to avoid a shutdown. Below the status bar is the main display section. This is where FlightView places most of the information used to operate the aircraft. This space can be configured as a split screen with the primary function, the screen that's most important, displayed on one side, and a secondary function displayed on the other. In this case, you see the main display section showing the PFD on the left and the MFD on the right. If the PFD is set as the primary function, the MFD will be replaced by other secondary functions, say the COM radio or transponder screens, when those are displayed. You can also run the display in full screen mode. In this case, the entire main display area is taken up by the primary function. When a secondary function is activated, it can either temporarily reduce the full screen display to half screen, or it can be configured to overlay the primary function. FlightView can also operate in full screen MFD mode. In this case, the MFD, our moving map display, takes up the entire width of the main display area. Below the main display is the optional engine bar. This section shows a readout of most or all the engine probes, senders, and transducers connected up to the engine monitor. At the bottom of the screen is the button bar. This is the main navigation system for the FlightView app. It displays up to 6 on-screen buttons. What appear in the buttons is context dependent. It changes depending on what primary and secondary functions are currently active. For example, if you were to tap the COM1 button, the system would load the COM radio screen, and the buttons would update to show COM radio related options. Most of the time, the button bar shows the main menu. For more options, you can tap the 6th button marked More. This loads a secondary list of menu options. When you're in a secondary menu, or when you have a secondary function active, you can return to the main menu and dismiss the secondary screen by tapping the first button, which is marked Exit. So now that you know how the screens fit together, let's cover a few of the basics of changing the display. Keep in mind that these are all temporary changes. If you want to make permanent changes to the layout, you'll need to use the options in the Appearance page under Settings, something covered in detail in the Configuring FlightView presentation. To temporarily toggle between full screen and split screen, tap the More button, then the Display button, then the button labeled either Split Screen if you're in full screen mode, or Full Screen if you're in split screen mode. This will immediately switch the display between modes. If you want to hide or show the engine bar, you can do so by again going to the Display menu and tapping the button marked EMS. The button will shift between active, orange, and inactive, in gray, and the bar will either appear or disappear as required. If you're in full screen mode, and you want to switch between PFD or MFD, or vice versa, you can use the Show button, again located under the Display menu. If you're in PFD mode, you should see a button marked Show MFD. In MFD mode, you'll see Show PFD. Tap the button and the system will display the desired screen. Tap it again to return to the other state. One last display mode. By default, FlightView automatically switches between day and night mode based on where you are and what time it is. If you ever want to override that, you can use the day and night toggle option. Simply tap day mode or night mode to switch as needed. Okay, so now you should have a pretty good understanding of the basic layout of FlightView. The next section takes a much closer look at each of the main screens and gives you some hints on actually using them while flying. By now you probably recognize this as the Primary Flight Display, or PFD view. This is the main flight instrument display, and it's where you'll spend most of your time while using FlightView. If you've never flown in a glass cockpit environment, it might look a bit intimidating. Don't worry, it becomes second nature very quickly, much quicker in fact than scanning 6 separate primary instruments and any number of secondary gauges on a classic panel. One of the biggest differences between a classic 6-pack and a glass display like FlightView is the size of the attitude indicator. If you're used to staring at a tiny AI, you'll find the attitude display in FlightView refreshingly large and easy to read. The blue and brown are the same as what you're used to. Blue is the sky, brown is the ground, and a white line separates them. The yellow chevron and pointers represent your aircraft. As the airplane banks, the roll indicator moves to display the attitude. In this image, you'll notice that the right wing is down, indicating a turn to the right. To get back to level, simply turn the aircraft to the left to take out the roll. The roll indicator at the top shows your actual angle. In this case, the aircraft is rolled 10 degrees to the right. The roll indicators show 10, 20, 30, 45, and 60-degree banks. The pitch indicator shown here uses the classic ladder format with degrees above and below the horizon point marked on either side. In this image, you can see that the pitch angle is nearly level, with the tip of the chevron being only slightly above the horizon line. The slip skid indicator, also known as the inclinometer or simply as the ball, is a small white line beneath the static roll pointer, that upward pointing white triangle. If the aircraft is yawing, you'll notice the ball moving right or left. As usual, you'll want to step on the ball to coordinate your turn or compensate for engine P-factor. Where older aircraft use round gauges, most glass displays use a more modern presentation called a tape. Here you see a stack of speed-related items which includes the indicated airspeed tape. At the top of the stack is the airspeed bug. This is used as a reminder of your desired airspeed. You can set the bug value using either on-screen controls or a knob on the flight bar controller. If you're using on-screen controls, simply tap the bug to display the on-screen rotary encoder. You can then spin the virtual knob left or right to adjust the value. Next is the indicated airspeed tape. The body of the tape, the numbers in the background, move up and down as the airspeed increases and decreases, giving you a good idea of the current trend. In the center of the tape is the current airspeed. This is the indicated airspeed. The indicated airspeed is calculated by FlightView's air data computer using inputs from your pitot-static system. On the inner edge of the tape are color bands that serve the same functions as the white, green, yellow, and red arcs on a classic airspeed indicator. White represents the range at which it's safe to deploy flaps. Green is the maneuvering range, the range at which full control deflections won't bend the aircraft. Yellow extends from the top of the maneuvering range to the aircraft's normal operating limit, and red indicates the never exceed point, or VNE. The values that control these are your V-speeds, which you can configure from the settings menu. Next down the stack is true airspeed. This is the actual speed the aircraft is moving through the air. This value is calculated using readings from the air data computer, most specifically the outside air temperature value. True airspeed is good for bragging rights, but do remember that your wings operate using indicated airspeed. Next is ground speed, your speed over the ground as measured by the GPS. If we lose pitot-static input, we can fall back to using ground speed in place of airspeed. Just keep in mind that ground speed doesn't include any impact of winds, so you'll want to give yourself a few extra knots when landing. At the bottom of the stack is the outside air temperature, or OAT reading. This comes from the air data subsystem by way of the digital thermometer mounted somewhere outside of your aircraft. FlightView uses OAT to help calculate density altitude and true airspeed. It also lets you know if you're facing a risk of icing, turning blue at and below freezing. On the other side of the attitude display is the altitude stack. As you might expect, this combines a number of different altitude values and settings. At the top is the altitude bug, which is both a visual reminder of your target altitude and also an input into the advanced autopilot system. If the autopilot is active, adjusting the bug pre-selects the altitude, and the autopilot arms the altitude hold mode. When the aircraft reaches the target altitude, the autopilot switches over and maintains the pre-selected altitude. The altitude tape, like its airspeed counterpart, moves up and down to indicate the altitude trend. The current altitude indicator shows your current barometric altitude in increments of either 10 feet or 10 meters, depending on the active altitude unit. This is the value FlightView uses for your MSL altitude and is based on the altimeter setting. Which is the next item down the stack? Altimeter setting, also called baro setting or QNH, is set in either inches of mercury or millibars. This, like the bug indicators, is an active control. You can either tap to select it or select it using the knob click function on the flight bar, then adjust its value. That said, you may not have to do that very often. By default, FlightView uses ADS-B METAR data to automatically update the altimeter setting. Next is GPS altitude. This is the GPS's estimate of your MSL altitude. If your GPS receiver has a good lock, this value is generally within 50 feet of the barometric MSL altitude. It makes a good cross-check value. If you see the GPS and baro altitudes diverge by more than 100 feet, you may want to check your baro setting. Next is AGL, or above ground level altitude. FlightView calculates the AGL value using terrain data, and if you don't have the terrain data loaded for your current location, this item will be disabled. If you have the Falcon landing coach installed, FlightView will switch over to using the laser when you're within 140 feet of the ground. Finally, at the bottom of the stack is density altitude, the altitude adjusted for temperature and humidity. Our air data subsystem uses the OAT probe to calculate this. It's quite useful if you operate out of high elevation airports or on hot days. Density altitude can have a major impact on aerodynamics and engine performance, and high density altitude at a short airfield can make for a bad day. Okay, on to the next instrument, the vertical speed indicator. This does exactly what you would expect, but it may do it a little bit faster than you're used to if you've been flying with steam gauges. The indicator shows your rate of climb or descent over a 3-second trend window, about twice as fast as a classic VSI. Above it is the vertical speed bug. At this point, I think you probably have a good understanding of bugs, so I won't spend much time on it. Note that this one is also both a reminder and an input into the advanced autopilot. Back over on the left side, you'll find the G meter. This shows how many positive or negative Gs the aircraft is currently experiencing. Note that the G meter is hidden on the half-screen version of the PFD, but the G-force alerts will still be active. In the bottom center of the PFD is the Horizontal Situation Indicator, or HSI. It's a combination of a compass, or directional gyro if you prefer, and a course indicator. At the top is the current ground track value, which is also displayed on the compass. Around the outside edge of the compass, you'll notice the cyan-colored track bug. This corresponds to the track bug value shown in the lower left-hand corner of the HSI. You can adjust this by tapping the track bug value or the compass value. You can then use either the on-screen encoder or the flight bar to adjust the value. The track bug, like the vertical speed and altitude bug, is used as an input into the advanced autopilot. In the center, you see the course pointer, the magenta arrow, and the course deviation indicator. In this case, you can see that the course is about 12 degrees to the right of the current track. You may also notice that the course deviation indicator, the center section of the arrow shaft, is just slightly to the left of the rest of the arrow. This indicates that the aircraft is slightly right of course. If you run the PFD in full screen mode, you'll have the option of adding a mini-map, which gives you a quick reference to nearby navigational details, the magenta course line, airports, navigation aids, traffic, etc. This is a great option for users who want to run a single screen in PFD mode. Do keep in mind that it isn't as flexible or as detailed as the half-screen or full-screen MFD, and it does not support touch to navigate. On the far right-hand side of the PFD is the navigation data display. This is populated when a course is loaded, and it shows key information about the course, including the next waypoint, final destination waypoint, estimated time en route, estimated time of arrival, and distance to go. Tapping either the next waypoint or destination waypoint button will cause Jeeves, the virtual co-pilot, to read off a briefing providing information about the waypoint. The PFD navigation bar is available only in full-screen PFD mode. In split-screen mode, the same data is available on the MFD's navigation data bar. FlightView has a basic timer function, which can be useful for time turns or other time-dependent operations. Tapping the timer button starts the timer, which is displayed in the upper left-hand corner of the PFD. The timer issues a loud beep every 1 minute and will continue to count minutes and seconds until stopped by tapping the timer button again. In the bottom right-hand corner of the PFD is a label that indicates the function currently assigned to the flight bar knob. You can switch active inputs by either tapping on the associated control, the bug or setting, or by clicking the knob currently assigned to the PFD. Doing this toggles between the various inputs in a clockwise circle around the screen. If you're running in a full screen PFD mode, you'll always use the knob on the right-hand side, just below the indicator. The left-hand knob is used to zoom in or out on the mini-map. FlightView is capable of generating alerts for over 50 different conditions. These are expressed as audio alerts read out by the virtual co-pilot and also as on-screen pop-ups. Alerts appear in various places on the screen depending on the layout. In full-screen PFD mode, alerts appear in the bottom right-hand side. A small window in the upper right-hand side of the PFD lists nearby airspaces, controlled airspace, military operation areas, restricted areas, prohibited areas, and defense airspace. The indicator shows both upcoming airspace, starting about 10 nautical miles out, as well as the designation of the airspace you're currently in, if any. Green-colored text indicates an airspace that's nearby but not likely to be violated given your current track and altitude. Yellow text indicates airspaces that you're either in or will be entering shortly given your current altitude and vector. If you have the advanced autopilot system integrated, you'll notice two additional indicators that appear when the autopilot is operating. The left-hand indicator shows the lateral mode, either bank, track, or nav. The right-hand indicator shows the vertical mode, either VS for vertical speed or ALT for altitude hold. A white label to the outside indicates any armed mode, a mode that will engage when the system reaches a given set of conditions. In this case, you can see that the nav mode has been selected, but is currently showing as armed. That's because the aircraft is too far off the course bearing to automatically engage navigation mode. The pilot will need to fly the aircraft to a track and position that lines up roughly with the course before the autopilot will take over. Here's a quick review of all the different interactive elements of the PFD screen, the things you can adjust. The mini map supports standard pinch and spread gestures to zoom in and out. The bug indicators and altimeter setting can be activated by tapping if you're using the on-screen controller, or by clicking the flight bar knob if you have a flight bar. One more quick note about using on-screen controls. I've mentioned the virtual rotary encoder several times. Here's a picture of it. It works like the scroll wheel on an old iPod. Place your finger on it and spin left or right to adjust the value. When you have it dialed in, tap OK. It isn't as good as the flight bar, but it's much better than trying to tap numbers in on a keypad. Trust me. Okay, onward to the MFD, or Multifunction Display, also commonly called the moving map. Where the PFD shows details of your situation, the MFD gives you a much broader view. It's here that you get a clear picture of nearby weather, air traffic, obstacles, terrain, and airspace. If you recall from the installation section, the MFD starts out with a base map. The base map gives you basic geographic boundaries, countries, states, oceans, lakes, and waterways, as well as terrain shading at higher zoom levels. Even better, it also allows us to switch into a street map mode that displays a very rich map with the names of towns, streets, and landmarks. Great for those "where am I?" On top of the base map, we layer all kinds of things, including an own ship icon. This blue pulsing aircraft outline represents your aircraft. In track up mode, it always points to the top of the screen. In north up mode, it rotates to match your ground track. A dashed line extends from the own ship icon to the edge of the screen, showing the current flight path. When operating at lower altitudes, FlightView displays obstacle icons. These are normally small gray Washington Monument looking things. At higher resolutions, FlightView displays the MSL elevation at the top of those obstacles. If the system detects a potential obstacle conflict, the icon is replaced with a larger yellow icon, and our old friend Jeeves gives us a friendly "Caution! Obstacle!" If the conflict isn't resolved, the icon turns red and Jeeves ups the volume, shouting, "Warning! Obstacle!" Obstacles are only visible at relatively high zoom levels, but the obstacle monitoring and warning system is always active unless you disable it. Even at high zoom levels, obstacles fade out once you get to more than 1,000 feet above the tallest obstacle currently in view on the map. Traffic targets work quite a bit like obstacles, but they also move, both vertically and laterally. The target icon has a numeric value superimposed above it. This is the relative altitude. The plus 15 on the icon pictured indicates that the target is 1,500 feet above your current altitude. Negative value indicates a target that's below your current altitude. A value that's either 0 or fairly close indicates a target that may very well be in conflict with you. If a target is climbing, or if you're descending and the target remains level, the system will add an upward-facing arrow. A downward-facing arrow indicates a relative descent. The traffic monitoring system continuously scans for potential conflicts, and will highlight those in red. If the conflict reaches the point of posing an actual danger to you, a traffic alert will appear on the screen, and Jeeves will start shouting, "Traffic! Traffic!" When this happens, it's usually a good idea to head in a different direction and/or change altitudes quickly. Traffic targets also have an identifier if the ADS-B data includes one. You can tap on the target and, if the aircraft is in the public registration database, get basic information about the make, model, and even owner. As I mentioned earlier, FlightView has a database that includes airspace, and by default that appears on the map. We currently show rings for controlled airports of class Bravo, Charlie, and Delta. We don't show anything for uncontrolled airports with class Echo airspace. We also depict special use airspace, including military operation areas, restricted areas, prohibited areas, and national defense airspace. The traffic layer contains all air traffic targets. You can manually adjust the scope of this layer in the Map Options Settings page. There you can adjust the diameter and height of the traffic monitoring zone. To reduce clutter, simply adjust the diameter to some useful range, like 5 miles, and set the height to plus or minus 1,500 feet. The system will screen out any targets outside of that zone, making for a much less complicated map. Under most circumstances, regional NEXRAD weather radar is uploaded over the ADS-B link approximately every 2.5 minutes. Continental updates, which provide a broad but low-resolution picture of the entire country, happen every 15. This isn't exactly real-time weather, but it's frequent enough to use for strategic, if not tactical, planning. NEXRAD is on by default, but can be removed by turning off the NEXRAD option on the Map menu. FlightView's MFD includes a lateral or profile view. This view shows what's ahead. Currently, it's focused on terrain, but future updates will add airspace and obstacles to the profile. Terrain at a safe distance below the aircraft is displayed in green. Terrain within 500 feet of the aircraft is depicted in yellow. Any terrain at or above the aircraft's current altitude is depicted in red. The profile supports 2 modes: Plan mode, which shows the elevation for an entire course, and Live mode, which shows the profile for the next 10 nautical miles along the current flight path. The outsized scale of the icons on the map can easily lead the user into misunderstanding the scale and distances that are involved. To help overcome that, we include a distance ring. The ring is a constant diameter, taking up half of the split-screen PFD, or 1/4 of the full-screen view. As the user zooms in and out, FlightView updates the distance caption to indicate the distance from the aircraft to the ring. This makes it much easier to estimate the distance to an airport, obstacle, or traffic target. An active course is depicted as the ubiquitous magenta line, which guides you from one waypoint to the next. The course line is displayed whenever a course is loaded. The active leg appears in magenta, while inactive segments appear in blue or gray, with blue indicating upcoming legs and gray representing completed legs. At the bottom of the map portion of the MFD view is the nav data bar. This is basically a horizontal version of the data bar found on the PFD. As with the PFD, you can tap the next waypoint and destination waypoint items for details on those points. The MFD exposes most of the information from the aviation database we downloaded during installation. One of the most important data elements is the list of airports. FlightView displays airports on the map using the standard dot with a cross iconography used by other charts. By default, airports appear in a kind of burgundy color. Airports with METAR data available are recolored to indicate the flight category at the airport. As you zoom in on an airport that's either the start point or the end point for a flight plan, the system will load an airport diagram. In some cases, these are FAA-produced official diagrams. At other airports, these are sourced from an open-source mapping project. The FAA diagrams include taxiway identifiers. The crowdsourced diagrams do not. As I mentioned, FlightView color codes airport icons depending on the flight category value of the local METAR. Green indicates VFR conditions, blue is marginal VFR, red is IFR, and magenta is low IFR. If an airport's METAR report is out of date or fails to decode, the airport will appear in the standard burgundy color. To make approach planning somewhat easier, FlightView adds extended center lines to all runways at the destination point in a flight plan, assuming that destination point is an airport. While FlightView's navigation system is purely GPS-based, we do include in the database, and on the map, a full set of active terrestrial navigation aids. These include VORs, VOR DMEs, VORTACs, and even NDBs. Tapping on a nav aid icon will display the name of the nav aid and the associated VHF frequency. You can also add nav aids to an existing flight plan or use the Direct To button to plot a course directly to a nav aid. At the top of the MFD is a scrolling compass. This indicates your current ground track, either in degrees true or degrees magnetic, depending on how the system's configured. Note that this always shows ground track, the aircraft's direction of travel, not the aircraft's heading. The MFD uses the same airspace status indicator as the PFD, letting you know what's ahead of you and what's around you. As with the PFD version, this box can extend to show multiple relevant airspaces. In the upper left-hand corner of the MFD is the north arrow, which also serves as the pan lock control. In track up mode, this icon rotates to point to north. In north up mode, it's static. Tapping this icon toggles the MFD between locked mode and pan or slew mode. In locked mode, the map centers on the own-ship position. You can zoom in and out, but you can't pan or slew the map. Tapping once on the north arrow places the map in pan mode, allowing you to move around the map by dragging. To return to the normal locked mode, simply tap the arrow once again. Most people use direct courses these days, but on occasion it can be useful to follow official airways. FlightView overlays either low-altitude Victor Airways or high-altitude Jet Airways depending on user preference. Airways can also be turned off from the Map Options menu. Here's a quick look at all of the active controls on the MFD, the things that respond to a tap or a click. Note that you can also zoom in and out using the standard pinch and stretch gestures or using the flight bar knob. Remember that airport icons are active. You can tap them for details, which are provided by the Airport Information popover. It includes 3 tabs, one for basic airport information, another covering weather if available, and a third for runways. The Airport Information dialog also allows you to either add the airport to an existing course or plot a direct-to course to the airport using the buttons at the bottom. The Info tab includes the airport's elevation, whether or not the airport has a control tower, the magnetic variation, and a list of frequencies. If your FlightView system has a remotely controllable radio, you can select any of the listed frequencies and the system will automatically tune COM1 to that frequency. The Weather tab includes all the normal data from the station's METAR report. The specifics vary a bit depending on what kind of automated equipment is reporting the weather and what's happening. The Runway tab lists runways at the airport and various useful facts about each, including the length, width, and surface. By default, all traffic is assumed to be left traffic, and any runways with a right-hand traffic pattern are marked as such. Tapping random points on the map also brings up a dialog box, the Map Features box. At the top are the coordinates for the tapped point. Below that are any airspaces that contain the tapped point, the nearest ATC center, and a list of nearby features. As previously mentioned, tapping on a traffic target will, if the target is in the U.S. Public Registry, open the Aircraft Details dialog box. This can be useful if you're trying to figure out if a friend is forming up on your wing or if those are F-16s on their way to intercept you. Okay, we're over 100 slides in now, and we're ready to start talking about navigation. You've already seen some options for basic direct-to navigation, done by tapping the map. Next up are some of the more formal means of navigating, using the nearest list, entering a direct-to destination, or creating a full flight plan. The nearest function is usually used in emergency situations, where you need to be on the ground at an airport with enough runway to land safely, ASAP. It lists the nearest airports, ordered by distance from your current location. It shows the distance in nautical miles, bearing, the length of the longest runway, the tower frequency, if any, and the flight category using the same green, blue, red, magenta coding as the airport METARs. To go to a nearest airport, just tap it. It will immediately be loaded and activated. The next option for navigation is the classic Direct To. Just tap the Direct To button, enter the FAA or ICAO code for the destination airport, nav aid, or intersection, and off you go. The final option is to create a formal flight plan. This is done by simply entering a series of waypoints using the same process as you use for Direct-to routes. First, tap the Add Waypoint button, enter the waypoint identifier, and tap Go. The point will be appended to the plan. Repeat as necessary for each of the points in your plan. If you want to insert points before or after an existing point, delete a point, or activate a point, you can do that using the Waypoint pop-up menu. Just tap on a waypoint and make your selection. It's worth noting that there's a difference between the Activate Waypoint and Direct-to Waypoint buttons. The Direct-to button replaces the current flight plan with a Direct-to course to the selected waypoint. Everything else is deleted. The Activate Waypoint button keeps the plan but forces the navigation system to sequence to the selected point. So here's a bit of a surprise given the VFR navigation banner at the top of the screen. FlightView has support for loading and flying GPS RNAV instrument approaches. Now that's not to say that FlightView is an IFR navigator. It isn't. The approach feature is for use in training to provide additional situational awareness when using an official IFR navigation system, and for backup used in emergency situations only. Any other use of this will probably land you in hot water with the FAA. With all of that out of the way, it's really easy to use. To get started, just tap the Load Procedure button. The system will load a list of RNAV GPS approach procedures available at your destination airport. If there are no RNAV GPS procedures, this list will be empty. To load a procedure, just tap it. Next, review the procedure plate to make sure you've selected the right approach. If not, you can tap the back button to select a different approach. Next, you'll need to select a transition, or pick vectors if ATC will be directing you to the final approach fix. Then, select minimums. Finally, tap the Load Procedure button to add the approach to your flight plan. The system will update your plan to include all of the procedure waypoints. It will also load the procedure plate into the map, allowing you to see the official FAA data and the FlightView course together. Note that the procedure waypoints at and after the initial approach fix are labeled with both the fix identifier and the minimum crossing altitude. To load a view of the full FAA plate, you can tap the blue Plate button. This will load a zoomable, pannable, scrollable view of the plate with a magenta overlay of your selected course. To dismiss the plate view, tap the Done button. Flying an approach also has some impact on the PFD. Once you reach the initial approach fix, precision lateral and vertical deviation indicators will appear, as will a thin magenta line on the VSI which shows the required vertical speed, or RVS. Matching your actual vertical speed to the RVS indicator should allow you to track the glide slope. Both the indicators and the RVS become more precise as the approach progresses. All of the approach-related features are currently experimental. We plan on adding a few missing pieces, procedure turns, holds, and missed approaches in a future update. To be able to access the approach features, you'll need to have a USB thumb drive with the approach database connected to your flight data computer. You also need to enable the feature from the Experimental Features page in Setting. Okay, we're at 115 slides now. If you're still here, thank you for your patience. We're in the home stretch. Next up is engine monitoring, and fortunately, while engine monitoring is very important, it's also fairly simple. FlightView has two engine monitor views, the engine bar view and the larger half-page display that can be called up on demand using the EMS button on the button bar. The bar is better for most things, but the half-page display includes one important feature that's not available on the bar. To go over the basics first, the EMS bar and page can display any of the data elements collected by the engine monitor hardware. The configuration of the engine monitor and the configuration of the display are both really out of scope for this presentation, but suffice it to say that both are quite flexible and can be configured to meet the needs of most experimental and light sport pilots. The one cool trick that the half page can do that the bar can't is leaning. To use lean mode, tap the button marked lean. You'll notice a set of yellow lines appear at the top of each EGT value. Begin leaning and those peak marks will begin to move up. When the first cylinder begins to drop, indicating that the peak has been reached, the display will stop showing EGT and instead show the delta from the peak point as a minus value. If you're running rich of peak, enrich the mixture until the temperature drops to the desired degrees below peak. If you're running lean of peak, lean the mixture until the temperature drops as required. Tap the peak button again to return to the normal view of EGT values. We've made scanning the EMS subsystem very easy. If everything is green or blue, you're good. The system only displays yellow or red if a value is outside of its nominal range. Off-nominal conditions will result in a color change in the EMS display, an alert pop-up, and a brief message from Jeeves letting you know that something isn't quite right. Okay, now we're on to COM radio interfaces, one of several remote control interfaces supported by FlightView. We can control up to 2 VHF COM radios. If you have 2 radios configured, you'll have buttons and status bar icons for COM1 and COM2. If you have only one remotely controllable radio, you'll have COM1. If you have no remotely controllable radios, you'll still have a button, now marked COM frequency, which lets you look up frequencies which can then be punched into your legacy COM. When the COM radio view is active, the button bar displays a number of shortcuts, including the Nearby button. Tap Nearby, and you'll see a list of nearby airports ordered by their distance from your current location. Tap one and it becomes the active airport. FlightView then loads a list of frequencies with function identifiers, things like tower, ground, approach, etc. Select the desired frequency and it will load immediately. Once an airport is selected, the most popular and commonly used frequencies are loaded into a set of quick access buttons, the orange buttons on the left side of the image. Not every airport has every option. If you select a very small airport, all you might get is multicom. However, most public airports have at least ATIS or AWOS, CTAF, and Unicom. You can, of course, enter frequencies directly using the keypad. You can also spin them in using the knob on the flight bar, but that's a joy best saved for very bumpy days where using the keypad is virtually impossible. A few other buttons make short work of returning to recently used frequencies, accessing frequencies associated with your current flight plan, and jumping immediately to the emergency or guard channel. The transponder interface is even easier. I only have one slide, it's that easy. Enter the squawk code using the keypad or the flight bar knob. Tap the button for the mode you want to use, and hint, it's almost always altitude. Jump back to VFR mode by tapping the VFR button, and ident by tapping, you guessed it, the ident button. That's all there is to it. Well, there's also the option to ident by tapping the transponder icon in the status bar, but really that's all there is. But I have saved the best for last, the autopilot. Now before I get into the details, I should explain that this screen and all of these controls and enunciators apply only to the advanced autopilot integration that works with a TrueTrack Vision and the Bendix King X Cruise. If you have some other autopilot that works with a basic NMEA RS-232 feed, you can probably do much of the same stuff, but you'll need to do it using the autopilot's control head. If that's the case, all you need is the NMEA RS-232 connection from the FDC and you're good to go. If you do have the advanced autopilot, great. The screen is where you control the modes, the system mode, the lateral mode, the vertical mode. It's also where you can access the level and 180 shortcut buttons. The lateral modes are bank, track, and nav. In bank mode, the system normally just flies level. If you have the flight bar connected, you can adjust this value, but it will return to 0 automatically the next time bank is invoked. Bank is also the default mode. It's basically just wing leveler. Track mode causes the aircraft to follow the track bug on the PFD. Simply adjust the bug and the aircraft will turn to follow the selected track. Nav mode's a bit more complicated. It causes the autopilot to follow the loaded flight plan, turning as needed at each waypoint. Our nav controller allows for GPSS, or GPS steering, which avoids overshoots at turns and makes for smoother rides. We also have a couple of options for vertical mode. Vertical speed mode attempts to hold a selected vertical speed. To climb, adjust the vertical speed bug up. To descend, adjust the vertical speed bug down. To fly more or less level, adjust the vertical speed bug to 0. This is similar to altitude hold, but a bit more forgiving in bumpy conditions. The other mode is altitude hold. If you tap the Alt button, the system will hold at your current altitude, whatever that is. A feature that's really only somewhat useful. What's more interesting is to use the altitude bug to pre-select an altitude. This puts the autopilot into an armed state. Adjust your vertical speed to climb or descend, and when the aircraft reaches the desired altitude, the mode will automatically switch from vertical speed to altitude hold. It's also worth adding a quick reminder that the autopilot mode is displayed on the PFD, with the lateral mode appearing on the left side and the vertical mode appearing on the right. Okay, final feature, and it's only one slide, checklists. You can create as many of them as you like, each with as many list items as you like. You can tag them to various phases of flight, and best of all, when you activate them, Jeeves reads them to you in his plummy London accent. You can disable that feature if it becomes annoying, but personally I kinda like it. Running a list is easy. Open the checklist view by tapping the checklist button. Select your list and away it goes. You can acknowledge each item by tapping it or by tapping the check, skip, or repeat buttons on the button bar. That's it. That's checklists. One final note on offline operations. If your electrical system goes out and the FlightView hardware goes offline, the app will do its best to switch over to reversionary mode using the onboard hardware. This can take a minute depending on how good the GPS reception is. It will also not work at all if your iPad doesn't have GPS hardware. GPS capabilities only come with iPads that have a cellular function built in. As always in an emergency, don't panic, aviate, navigate, and communicate. Okay, so that's it. Thanks so much for sticking with me all the way to the end. I hope that was a useful hour of your life. For more information on installing FlightView, check out our installation tutorial. For details on configuring all the interesting stuff in the settings menu, which I totally ignored in this presentation, check out our even more entertaining Configuring FlightView presentation. Thanks again, blue skies, and fly safe.